Hello, for our second part of this lecture, which are exercises of section 3.4. All right, I'm going to start by solving a couple of examples from 11 to 20. The question says, find by hand all critical numbers and use the first derivative test to classify each of those critical numbers as local max or local min or neither. All right, so let's look at number 11. Y equal x4 plus 4x cubed minus 2. To get critical numbers, we have to get the derivative, which is 4x cubed plus 12x squared, which is 4x squared into x plus 3 in simplest form. Then we have to find the zeros of that derivative, which means either 4x squared equals to 0, which means x equals 0, or x plus 3 is equal to 0, which means x equals minus 3. Find y prime undefined. This is not applicable, again, because we are working with polynomials. So how many critical numbers do we have? 2. How do we classify? How do you apply the first derivative test? To apply the first derivative test, you do a table of variation over the domain of the function. This function is a polynomial. Its domain is all real numbers from minus infinity to infinity. Then we order from the least to the highest critical number. Then we study the sign of f prime. Those are zeros of f prime, and we study from f prime the behavior of f. See, if we take a value here, which is minus 4, and substitute it in y prime, this is always positive. Minus 4 plus 1 is negative, so the answer is negative. Minus 3, 0, you choose minus 1, you will get positive. And after 0, you choose like 1, you get also positive. All right, so never assume it's negative, positive, negative. It alternates. No, it could be anything. You have to take and test at each and every one. Do you notice the change here from decreasing to increasing? When a function changes from decreasing to increasing, according to the first derivative test, what do we have here? We have a local minimum point. We're no longer talking about absolute. We're talking about local minimum points over here. At 0, since the monotonicity does not change, the function was increasing, it continued to increase. This means we have no local max or min. Okay? It is conclusive. I can tell it doesn't have a local max, so it doesn't have a local min, because the monotonicity does not change. The function was increasing, it continued to increase. Okay, in this scenario, so what do I say? I say that we only have this function, f, has only a local minimum point that is minus 3. And what do we get here? It's f at minus 3. Take minus 3 and substitute it in this equation that we have over here, which gives us minus 3 here times minus 3 cubed plus 4, so 1 minus 3 plus 1 times minus 3 minus 20, so minus 29. So this is the only local extreme values that this function can attain. All right, I'm going to solve another example. The example that I'm going to solve is example number 13. Again, to show you how you handle questions that involve exponentials. If you have practiced properly how to get derivatives, so we want critical points. Derivatives here, they need product rules. So 2x e minus x plus x squared e minus x. The derivative of e minus x is e minus x times minus 1. So this gives me 2x e minus x minus x squared e minus x. See, whenever we find the derivative and we want to find the critical numbers, we have to solve this derivative equal to 0 and this derivative undefined. To say that this derivative is equal to 0 and to solve it as is, it's too complicated. That's why the best thing to do when we have such a scenario is to take common factors. And when we have exponentials in a product rule, the exponentials, their derivatives are exactly the same. So if we take the exponential and then we differentiate it, we get exactly the same value. So this will be part of our common denominator, common factor, in both cases. And x, so what's the common factor? xe minus x, what do we have left? 2. xe minus x, we're left with 2 minus x. We want to solve this equal to 0. See, this is easy now when it's factored. For this to be equal to 0, either x is 0, or e minus x would be 0, or 2 minus x would be 0. X equals 0 solved already. E minus x can never be equal to 0. Why? Because exponentials, they are always greater than 0. They are never equal to 0. And 2 minus x equals 0 means minus x equals minus 2, which means x equals to 2. Is this ever undefined? No, because e is defined for all values, x is defined for all values, and 2 minus x is defined for all values. You tell me e minus x is defined for all values. Remember, e minus x is 1 over ex, which is defined for all values that you can think of. So what are my only critical numbers? 0 and 2. So I will write here y prime undefined is also not applicable. All right, so always remember. I had students in the quiz write e1 over x as e to the minus x, which is not, of course. So careful, they are not the same quantity. If you want to write this and change it to power, it will be x to the power minus 1, not minus x. So please be very careful about these simple things. And now that we have this, how do we get our table of variation? So let's do a table of variation. So x, what is the domain of this function? The domain of x squared is all real numbers. The domain of any exponential is all real numbers as well. So the domain is all real numbers. Okay, so, and we write here from minus infinity to infinity. 0 and 2 are my critical numbers. I check the sign of y prime, the 0 here and the 0 here, which will give me the behavior of y. See the sign of y prime now for a value less than 0, like minus 1. This I don't have to worry about because this is always positive. Minus 1 times 2 minus minus 1, which is 3, is negative. So the first number is a negative number. Then from 0 to 2, I choose 1. At 1, what happens? 1 times a positive number, 2 minus 1 positive as well, we get positive. For a value bigger than 2, like 3, I take it and I substitute it here. I get 3 positive, positive, 2 minus 3 negative. So the answer will be negative. Did you notice what's happening here? It was decreasing, stopped, start to increase. What do we have? A local minimum. What is that local minimum? It has x equals 0 and y equals f of 0. Here it was increasing, it stopped, it started to decrease. What do we have? We have a local maximum where at 2 f of 2. What is the function f of x? It's x squared e minus x. So that's why it is 0. 0 e to the power 0, which is 1. So we get a 0. Here 2. 4 e to the power minus 2. So 4 over e squared. Those are our local extreme values of the function y equal x squared e minus x. All right. Let me see here. Let's look at number 27 to 32. I'll just show you what the question is all about. It's sketch a graph of function with given properties. I'm not going to solve these problems because you can solve them the way you want. But I'm just going to tell you what it means. See, many students come and say my answer did not turn out to be the same as the book. There are millions of functions for each scenario. So when I say f of 0 equal 1, f of 2 is 5, f prime of x negative for x less than 0 and x greater than 2, or positive for 0 between 0 and 2, I'm not saying anything except that the function is decreasing for values of x smaller than 0 and bigger than 2. It's increasing between 0 and 2. And I'm just giving two values, which are f of 0 and f of 2. The rest is uncontrollable. So if I just want to graph this one, let me fix back things. So if I just want to work with number 27 for you to understand, it's just a basic thing. Between it, you can do whatever you want. F at 0 is 1. F at 2 is 5. And they're saying that f prime of x is negative when x is less than 0 and x is greater than 2. So when x is less than 0 here, and when x is greater than 2 here, what's happening to the derivative? It's negative. This means, what do I know about the function f? I know that it's decreasing. How it's decreasing, I can't tell. They didn't give me enough information. So I just draw it the way I want. I know it's decreasing here and decreasing here. I draw it the way I want. I don't have to draw it like this. I draw it decreasing. You choose. You can choose to be decreasing concave up. It can be decreasing concave down. Whatever it is, as long as it can be decreasing as a straight line if you want. Doesn't matter. And here it can be increasing. For example, I'll draw it here increasing as a straight line. No one told me anything about the function. They just told me simple things. F prime is negative less here. Is it? Yes, because it's decreasing. F prime is negative here. Is it? Yes, because it's decreasing. F prime is positive here. Is it? Yes, because it's increasing. Is f of 0 equal to 1? Yes. If f of 2 is f of 2 equal to 5? Yes. So did I do all that they asked from me? Yes. Is this the only function I can draw? Of course not. You can draw whatever function you might think of. This can be straight, this can be like this can be concave down, whatever way you want. That's why how many options are there to cover what they are asking from us? So many options as much as you imagine. All right. The other thing I want to work in this actually, that's it for this section, I think, because the rest we will mention them again later on. All right, so let's move to section 3.5.